So we said at the beginning of 2.3 that a function is continuous if you can draw it without picking up your pencil. So what does that mean? It means that the graph moves without any skips or holes or jumps, anything like that. So we talked a little bit about the intermediate value theorem today, kind of like this idea of baby carrots. If we know two output values on a function, and we know that the function is continuous, that means that somewhere in between, here's my two output functions, somewhere in between the two x values that made those two y's, that the function must cover all of the in-between y's. There might be extra y's that get covered, but for sure we're going to have to cover all the ones in between the two y's that we know. So the formal statement of the intermediate value theorem, it's here, it's going to go on your important facts paper, it absolutely will be tested on the AP test. If f is continuous on the closed interval a to b, then f takes on every value between f of a and f of b. Suppose k is any number between f of a and f of b, then there's at least one number c in the interval a to b, such that f of c equals k. So just a couple of notes on some of these symbols. This notation, the interval a to b. When I use the brackets there, that means a and b are included. So for this theorem to work, I'm guaranteeing that f is continuous from all the way from x equals a to x equals b with a and b included. So no skips or jumps at the endpoints either. It's essentially what I said earlier. If I know two y values, two outputs, call them f of a and f of b, and there's some y in between, then I know, which in this case we're calling k, there's some place in between a and b where your y is going to have to cross through k. So, important idea number one. The intermediate value theorem is an existence theorem. It tells you that at some point between a and b, you will find a c, which is the input that gives you an output of k. It does not tell you how to find it, or doesn't guarantee you the number of times it could happen. It could happen multiple times. It could happen infinitely many times. So, existence theorem. It just tells us that it must happen at least once. Here, in the intermediate value theorem, is k an x value or a y value? Is it an input or an output? Well, when I look at this last part here, I'm guaranteeing that there's a c such that f of c equals k. K is an output. That means k is a y value. C is the input to the f function that makes the output k. So c is an input. C is an x value. So this picture, I think, kind of sums it up. If you know two ordered pairs, so this is a comma f of a, and here is b comma f of b. It implies that a and b are inputs, they're x's, and f of a and f of b are outputs, they're like y's. I missed a parenthesis there, I missed one here too. So f of b and f of a are the two y values you know, and k is some other y value that you're interested in. Like I asked, we said Rami was born 22 inches, he's 66 inches now. Has he ever been 50 inches tall? Well, the 22 and the 66 are two y values that I know. The 50 inches is some other y value that I'm interested in knowing about. So, since that y value I'm interested in is between the two y values I know, yeah, then there must be some age, some x, some age at which Rami was exactly 50 inches. Now you're famous, Rami. Okay, so two big things that sometimes get left out. This is only true if we can guarantee that our function f is continuous. If there's any chance that f has holes or skips or gaps, then I can't make the guarantee that there's some c whose output is k. And, okay, so the k has to be between the two y values that we know. That part is not the part that's sometimes missed. The other part is the c that we're looking for, that we might be looking for, the the input that makes the output we want has to be between the two input values that we started with. So the K, the output we care about, is between the two outputs we know, but also C is between A and B. So C is an input, it's between the two inputs we knew. K is an output, it's between the two outputs we knew. Here I suggest you circle on the graph any ordered pair for which f of c equals k. That's going to be any place where the f function crosses our dotted line, our horizontal line, y equals k. So it happens here, and here, and here. I'm going to suggest that as you begin to practice intermediate value theorem problems, that you make a picture, make a graph for everyone, at least while we're still beginning. So let's talk about this example down here. Oops. One more time. There we go. If f is a continuous function and f of -1 is 2 and f of 5 is 4, explain why there must be a value c for which f of c equals 3. So I'm going to make a graph to convince myself this is true, and then I'm going to show you how to write up your answer using the intermediate value theorem. This write-up is not anywhere, at least that I have found, in your textbook, but is absolutely something you would be expected to do on the AP test. The stuff in your textbook about intermediate value theorem, while it is all true, it's not a good indicator of how you're going to be tested on it on the AP test, which is why on the back side of this page, you'll find 3 practice problems. They're actually released AP problems. So, like I said, I'm going to make a graph to convince myself that there must be a c for which f of c equals 3. So I know f of -1 equals 2. That means when x is -1, y is 2. And when x is 5, y is 4. So 1, 2, 3, 4, 5. And I know my function f. So far I only have 2 points on my blue function f. But I know f is continuous, and I know it contains those 2 ordered pairs. So my question is, am I convinced that there is some x value that's going to give me y equals 3? So here's y equals 3. So you just have to ask yourself, are you convinced that if I connect the 2 blue dots with a continuous function, am I going to have to cross through the purple line? I hope you're convinced. It doesn't matter how curvy or bumpy or pointy or crazy you make your function, as long as it's continuous, which means you don't pick up your pencil when you draw it, then when you connect those 2 blue dots, you're going to have to cross through the purple horizontal line. So once I am convinced of this, I'm going to show you how to write up your answer using the intermediate value theorem. All right, so there's 3 big parts to our answer, our write-up, to explain why there must be a value c for which f of c equals 3 using the intermediate value theorem. First, we have to convince the reader that we checked that the function we're going to try to apply the intermediate value theorem to is really continuous. Because if I can't guarantee that f is continuous, then I have no business trying to use the intermediate value theorem. It's just not allowed. So it's pretty easy here, and it's sometimes this easy on the AP test, but you'll notice that we were told right here f of x is a continuous function. So if this was the AP test, nobody would argue with your statement here, since f of x is continuous, because we were told it was continuous, on the interval that we care about. So interval means like a domain section, and that's the domain of like the interval from between the 2 x values that we know about. And we know about where x equals -1 and x equals 5. And remember, I'm using closed brackets because I have to include the endpoints. F is continuous everywhere, so I can choose any subset, any sub-interval that I want. I've chosen it to match, like -1 and 5 are like my A and B. So this is like my A and B. So since f of x is continuous, so I've checked that the hypothesis is true, and the next thing I need to do is prove that I have one y value that's above the y value I care about and one y value that's below the y value I care about. So this is what I would type next. And f of -1 I know is equal to 2, and I have to convince the reader that I get that that's less than the y value I care about, because 2 is under 3. I need one that's below, is less than 3. And f of 5, f of 5, which I've been told is 4, f of 5 is 4, which is above, so bigger than 3. So that's my second line of my write-up. So f of x is continuous on the interval -1 to 5, and f of -1 is 2, which is smaller than the y value I care about, and f of 5 is 4, which is bigger than the y value I care about, then so since those things are all true, the does not need a capital because I haven't finished my sentence. You could write intermediate value theorem. You can also write capital I, capital V, capital T for intermediate value theorem. They'll know exactly what you mean. Guarantees, notice the spelling of guarantees, that there is at least one C. You have to write here that you know the C has to be between A and B. So in this case, our A is -1 is less, -1 is less than C, which is less than the other input value we know, which is 5. For which f of C equals the y value we cared about was 3. All right, let's see if I got it all. Since f of x is continuous on -1 to 5, and f of -1 equals 2, which is less than 3, and f of 5 equals 4, which is greater than 3, the IVT guarantees that there is at least one C. C must be in between -1 and 5, for which f of C equals 3. Final answer.